Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for the instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of remote sensing, platforms, sensors, and fundamentals of electromagnetic radiation. Remote sensing is technology used to collect information about the Earth's surface without physically touching it. GIS or Geographic Information System, which helps engineers to store, process, analyze, and display spatial type of data digitally. In civil engineering, these technologies are extremely useful for marking the alignment of highway, roadway, railways, dam site selections, urban planning, watershed management, and environmental monitoring. Remote sensing and GIS improves the planning efficiency which provide accuracy of geographical areas. The science and the art of obtaining information which is the most important objective for the data collection for remote sensing. That acquired data which will be useful as a input for the digital elevation model, digital surface model or digital terrain model likewise. Why we are using that data? Just we have to cross check the existing geoid earth or the material which are present on the earth surface with reference to its elevation. So we can see from ground surface biologically through our eyes with the visible light spectrum, or we can use some technology like sensors or satellites where rays are emitted from that satellites and the data will be collected. The three pillars of observations, or we can say that the data collection: first is the energy source, that is sun. Second will be the target, that the rays emitted from the sun and incident on the material or body on the earth's surface with reference to its geoid curvature. And third one will be the sensor who impact or emits the ray. Energy source which provides the illumination to light up the target. This can be natural solar radiation, that is the passive sensors, or artificial microwave pulses, that are the active sensors. Secondly, the target, the earth surface feature, that are rock, water, vegetative material, or any structure like concrete that reflects or absorbs or transmits the incoming energy which is emitted from the energy source. It may be passive source or it may be active source. And third one are the sensors, the precise optical or radar instrument that records the altered energy returning from the target. The process begins with an energy source, usually the sun, which emits electromagnetic radiation. This energy travels through the atmosphere and intersects with surface objects. Objects reflect or emit the energy depending on their physical properties, and sensors record this information. The collected data are processed digitally to generate maps and models useful for engineering planning and analysis purpose. The journey of signal, where A, B, C, D, E, F, G. These are all the process components. A will be the source of energy, that is sun. B, where atmosphere or the atmospheric window, where energy travels through a vacuum and atmospheric layers, just like gases or any moisture content or any wind facing scattered. Third one will be the structure of, just like any dam structure, where the target is selected to collect the information. The energy strikes the earth material or any object and is uniquely modified by surface materials. At the same time, that incident energy from A to C through B, that will be some energy is absorbed and some of the energy will get reflected. That reflected energy is received by the sensor, which is maybe a satellite or which is maybe a drone. That are the platform captures the reflected or emitted energy. After that, there will be a transmission phase, that is raw data is beamed or travel to ground receiving stations. So ground receiving stations are at the E, where they store the data after the transmission. The antennas of the receivers receive the whole data for the further processing activity. Processing units are interconnected to that receiving station, and that processing unit process the whole data which is collected with reference to the objective decided or the queries assigned by the user. In the processing unit, there are n number of data storages or analytics or algorithms. With reference to that algorithms, the whole data will be as an import for the process in input phase. After that, processing phase will be there. With reference to that processing, the actual output will be displayed as an application for the user. So processing where signal is converted into digital imagery, and in the application, engineers extract actionable insights, or we can say that the outputs for project design. The physics of signal, that is electromagnetic radiation, just like EMR. What is meant by EMR? Energy propagated through space into the form of advancing, interacting electric and magnetic fields. So remote sensing depends on electromagnetic energy for data collection. Electromagnetic radiation travels as waves with specific wavelength and frequency characteristics. Different surface materials absorbs, reflects and emits different wavelengths of energy. So to understand the EMR, which is extremely important because remote sensing sensors are designed to detect specific portions of electromagnetic spectrum, so that with reference to the x, y and z axis, we can check here x axis which give the direction of propagation, y axis where wavelengths are there, and for z axis there will be a magnetic field. So with reference to three domain, we can check the electromagnetic radiations as per that wave theory equation. C is equal to lambda into V. So C is the speed of light, lambda is the wavelength into frequency. Why particle theory is there? Because the electromagnetic spectrum includes gamma rays, X rays, ultraviolet rays, visible light, infrared and microwave radiation. So there are n number of rays are there. Visible light forms only a small part of the entire spectrum which is detectable by the human eyes. Infrared wavelengths are extremely useful for detecting moisture conditions, vegetation health and thermal properties. Microwave remote sensing is valuable because it works even during cloudy conditions and at night time also, which make it useful for flood monitoring and terrain mapping. So particle theory, where electromagnetic radiation also behaves as a stream of photons, where energy is inversely proportional to the wavelength. That means shorter waves is equal to higher energy. Electromagnetic radiation spectrum with reference to the atmospheric windows. Electromagnetic radiations are of started from the gamma rays, X-rays, ultraviolet rays, then visible light, infrared, then microwave waves, then radio waves likewise. So the portion above to that main line is includes that the atmospheric absorption, atmospheric windows and atmospheric overlay. Atmospheric absorption is by the signal block. Here the visible light is from 0.4 to 0.7 micrometer, where a tiny fraction of the spectrum which will be only the visible part from our naked eye. Other all rays are not visible to our naked eye. We have to check that rays with reference to some technology, just like some instruments or advanced instruments or tools for the sake of our interest. Here infrared, which is shown as IR, reflected infrared maps vegetation and moisture. That are reflected or infrared conditions are detect that vegetative material or moisture content. Also the temperature also we can check with reference to the heat dispersion. Then microwave, that is radar, 1 mm to 1 meter long wavelengths capable of penetrating cloud cover and dense vegetation. That radar is most important for the defense purpose. We can monitor or we can investigate the area. To improve the image quality and accuracy, atmospheric correction techniques are applied during image processing. Current wavelength regions known as atmospheric windows allow energy to pass through efficiently. The relay scattering mainly affects shorter wavelengths such as blue light. As electromagnetic radiation travels through the atmosphere, some energy is absorbed while some energy is scattered by due to the gases and the particles available in the atmosphere. Means the interaction between electromagnetic radiation and the atmosphere, which is the most important phenomenon to study, the impact of electromagnetic radiation and its effects. The atmospheric filter, that is scattering and absorption. Three conditions are there: relay scattering, Mie scattering, and non-selective scattering. The diagram itself suggests that relay where particles much smaller than wavelength, which causes blue skies. In Mie scattering, particles roughly equal to wavelengths, that means dust and smoke. And the third one, non-selective scattering, where particles much larger than wavelengths like clouds, fog, which affects all bands equally. Due to these three scattering, the actual electromagnetic radiations disturbs, and they may check their path, or they may get scattered, or they may get absorbed. Likewise, the electromagnetic radiation reaches to an object, the part of energy is gets reflected, part of energy may get absorbed, or the part of energy may get transmitted. So different materials show different spectral behavior depending on composition and the moisture content. Just example, water absorbs most infrared radiation, while vegetation strongly reflects near infrared energy. So these spectral characteristics help engineers to identify land cover, soil condition, and water resources. So scattering is the unpredictable radiation, or we can say that the unpredictable redirection of electromagnetic radiation due to some particles which are suspended in the atmosphere with reference to its atmospheric layers, and absorption where the total loss of energy to atmospheric constituents. What are the atmospheric constituents? Ozone, carbon dioxide, water vapor, just like gases which are above to the earth's surface and below to the clouds before it can reach to the sensor. Target interaction and spectral signatures. We can see that there is an object, there is a incident energy in the yellow color. After that, most of the energy gets reflected, which is shown with reference to the purple color, and at the same time there may be a absorption, that is emitted later as heat. At the end, transmission light through shallow water, means when the earth surface which having some vegetative material, some water material, or some soil material, likewise the material which is available on the earth surface, the amount of incident energy changes the reflection criteria, absorption criteria, or transmission criteria, or we can say that the amount. Likewise, reflection may change due to, if water is there, then large amount of reflection, if soil is there, less amount of reflection. Likewise, in the soil, energy may get absorbed, in the vegetative material, energy may get transmission or transmitted for photosynthesis purpose. With reference to the graphical representation point of view, if we check the spectral signature curve, the graph shows that the wavelength on the x-axis, they are the visible to infrared rays with reference to the percentage of reflectance. Means if water is there, then the reflectance through the water is minimum. But with reference to the healthy vegetative material or vegetation point of view, as wavelength increases, the percentage of reflectance also increases. That is the purple line. Reference to the dark dry soil, or just like the yellow line, at initial level, as wavelength increases, the percentage of reflectance also increases, but moderately. So this spectral signature curve is most important point to study the impact after incident energy of reflection, absorption, and transmission. The spectral signature curve is defined as the ratio of wavelengths with reference to the percentage of reflectance. Every material reflects a unique combination of wavelengths across the spectrum. By charting or by channelizing these unique reflectance curves, engineers can identify surface materials remotely and easily. Platforms, that are the stages where we can install the sensors, or we can take the data or collect the data with reference to the sensors. The earth surface with reference to its curvature, then we are installing advanced digital instruments, or just like the receivers on it, on the surface of the earth, with reference to drones, with reference to aircrafts, with reference to satellites, with reference to its orbits, we can take the aerial images or satellite images. Likewise, The satellites continuously collect the Earth observation data over large geographical regions. Satellite imagery is widely used for land use mapping, urban expansion studies, flood monitoring, and geological investigation. Polar orbit satellites move around the Earth and provide detailed global coverage. Geostationary satellites remain fixed relative to Earth and are mainly used for weather monitoring and disaster management. So basically three types of satellites are there: geosynchronous satellites, geostationary satellites, and polar satellites. Polar satellites are revolving around the pole. Geosynchronous satellites are revolving along some oblique angle with reference to the equatorial plane, and geostationary satellites are revolving around the equator. Likewise, each and every satellite play its role of data collection for the respective objective. Here, satellite, that is geostationary, fix over one location for continuous weather monitoring. Satellite low Earth orbit with reference to the orbit. Polar or sun synchronous orbits for global terrain mapping. Some airborne satellites are there or sensors are there with reference to high detail regional mapping or some cloud operations. And ground based satellites are there close range to the structural monitoring and sensors, just like the drones. The engineering trade-off point of view, higher altitude is equal to greater spatial coverage area but lower spatial detail. Means it's as you go higher altitude, then the greater spatial area will be covered but you get lower spatial details. Means if you have to collect the image clear or data clear, then we have to collect the data from near to the earth surface. With reference to the sensor, there are two types of sensors: active sensors and passive sensors. Passive sensors, they are the listeners. Active sensors, they are the flashlights basically. Now, what is the mechanism for passive sensors? They records naturally occurring electromagnetic radiation, just like reflected sunlight or emitted thermal heat. What are the pros for passive sensors? Have the simple architecture. They provide natural color and multispectral data. But what are the limitations? They operate strictly in daytime only, completely blocked by covered of the clouds. Means if the cloudy atmosphere is there, then passive sensors are not feasible to collect the data. Just like the examples of optical cameras and thermal radiometers, where sun is the main source of energy in passive sensors. But while in active sensors, the mechanism for active sensor is the which generates its own energy signal and which transmits and measures the backscatter or the data. What are the pros for the active sensors? We can collect the data 24 by 7 and day and night time. So operational active sensors are most important for 24 by 7 for each and every data collection and monitoring purpose. They are easy to penetrate clouds and forest canopies also. So with reference to dense forest or with reference to cloudy atmosphere, we can collect the data. What are the limitations for active sensors? High power requirements and complex data processing. What are the examples? That are LiDAR or synthetic aperture radar, that is SAR. In day-to-day civil engineering point of view, if we have to study the sensor, then we can check the passive sensors for small scale area. But for the any construction point of view or any project point of view, detailed survey point of view, we have to prefer active sensors which cover large area. Image quality, the four resolutions, basically types of resolutions are there: spatial resolution, spectral resolution, temporal resolution, and radiometric resolution. Spatial resolution determines the size of smallest object visible in an image. Spectral resolution indicates how finely a sensor can distinguish different wavelengths. Temporal resolution refers to how frequently a satellite revisits the same area. That is temporal resolution, day 1, day 16, day 32, means the cycle is of 16 day. And radiometric resolution, that how many shades of data can we distinguish based on some data storage, that is 8 bit is equal to 256 values. Means the spatial resolutions, spectral resolutions, temporal resolutions and radiometric resolutions are most important for the processing point of view, where the smallest data or the ground data is also considered with reference to its imagery. Spectral resolutions divide the whole geodetic earth with reference to its layers or with reference to its bands, so that we can take each and every band for the comparative analysis. The earth observation fleet. Now we see the three platforms of satellite, or we can say that the types of satellite. Just we will go one by one. First is the Landsat. Second one will be the Sentinel 1 and 2. Third will be the Cartosat or IRS, that is of ISRO India. Sentinel 1 and 2 is of European Space Agency, and Landsat is of USA and NASA. Means these all satellite programs are launched by respective, we can say that the country or agency, for the sake of the data collection or the disaster management or any other application point of view. If we use that type of platforms for data collection, then we have to install some sensors, so that sensors collect the data effectively and efficiently with reference to its purity. Sensors for Landsat are passive and optimal thermal sensors with spaces of 30-meter spatial resolution. We are using that Landsat data for the longest continuous space-based record of Earth's land, which is for tracking the decadal land cover change and broad geological mapping all over world. For the Sentinel 1 and Sentinel 2, where European Space Agency will be the monitoring agency, they have the sensors of active SAR, synthetic aperture radar, Sentinel 1, and passive optical for Sentinel 2. Here Sentinel 1 and Sentinel 2, they are with the high resolution of 10-meter, and they collect the data efficiently. We are using that Sentinel 1 and Sentinel 2 data continuously for all weather conditions, radar monitoring, and high fidelity vegetative or soil mapping conditions. For Cartosat or for IRS, which is operated by ISRO India, where high resolution stereoscopic optical sensors are used based on some capabilities or responsibilities or some assigned program, where sub-meter spaces are used as a resolution point of view. For what purpose we are using that Cartosat? For the precision cartography, terrain analysis, topographical condition study, detailed terrain modeling, and urban infrastructural planning. Here we can see the tectonic mapping and field observations. These are the geological characteristics. The structural geology and tectonics are the plates on the earth's surface or below to the earth's surface. Aerial and satellite imagery are critical for mapping complex folded strata or the area which is beneath to the earth's surface or in the mountainous region. We have to detect major strike, slip, fault, folds, that is geological characteristics for the distance, so that we can check the ground conditions below to that earth surface. The geophysical correlationship in between them is studied with reference to some advanced tool like remote sensing and GIS. Remote sensing acts as a visual base layer combined with gravitational and magnetic anomaly data to locate subterranean features like salt disappears and iron deposits. We can collect the data on raw point of view, where the exact topographical conditions or geological conditions, topographical mapping, textures, patterns are studied, where utilizing remote imagery to map lunar geology which impact structures and mere topography where traditional fieldwork is impossible. Likewise, we can take our decision as engineer which site is suitable for the foundation of any dam like structure or for any roadway or railway lines. For civil engineering point of view, here we can see the digital elevation model. With reference to that digital elevation model, we can plan our civil engineering projects for its 100-year policy of life. We have to mark some landslides risk zones. We have to take care of the ridge lines, valley lines, then flood lines likewise. So infrastructure routing, site suitability and geohazards, water resource management, urban planning, these are all the civil engineering project applications. In infrastructure routing, selecting optimum cost effective corridors for highway, railways and pipelines. For site suitability and geohazards point of view, we have to identify the landslides prone slopes and active fault zones before laying structural foundations of any structure. For the water resource management, mapping floodplains, calculating reservoir capacities, and delineating watersheds boundaries to define effective dam and drainage systems. Last but not the least, urban planning point of view, monitoring the impervious surface expansion and urban sprawl using high temporal resolution data. These technologies provide valuable spatial information for planning, design, and construction of engineering projects. Remote sensing and GIS reduce uncertainty, improves decision making, and support sustainable infrastructure development. In modern civil engineering, we rely on geospatial technologies for efficient project execution. To understand the remote sensing and GIS, which is most essential for each and every civil engineer nowadays. Stay tuned, guys. Happy learning.